our next speaker, that's Grace Olivier. She's a PhD student from OSU, and she's going to be talking about a self-consistent model for the ionizing spectrum of Reionization-Era analog galaxies. Take it away, Grace.
Yes. Thank you so much for that introduction. I'd like to thank the organizers for giving me the opportunity to talk to you today. I'm going to be talking about this work that I've been doing with Danielle Berg and John Chisholm at UT Austin. Well, I am starting my final year of grad school at Ohio State. So we're talking about Reionization-Era analog galaxies in this talk. And we know from the observations of higher redshift galaxies that high redshift galaxies are probably extreme emission line galaxies. This lens galaxy has extreme helium-2 emission that does not fit with any of the rest of the stellar models that fit the rest of this galaxy. So it tells us that Reionization-Era galaxies probably have other extreme emission lines similar to this. And these emission lines really help us by telling us what is happening in the ionizing spectrum. For example, helium-2 is ionized by photons that are 54 eV or greater, and we are calling this the very high ionization zone because it really surpasses the regular standard three-zone model of ionization zones. And there are just all of these emission lines are telling us what is physically happening in these galaxies. Since we're studying analogs, we have the option to actually look at both UV spectroscopy and optical spectroscopy, so we can study all of the lines that are available to us so we can get a better, fuller understanding of what's happening in these analogs to reionization galaxies. So the two analogs we use for this work are J104457 and J141851. They are the two highest equivalent width measurements of carbon-4 and helium-2 in the local universe. And they're very small, compact, metal-poor galaxies. As you can see, J14 here, it fits within the aperture of COS almost completely. And the COS spectra on the left give us amazing emission lines like helium-2 and carbon-4 that are just booming. You can also see that the helium-2 velocity structure is very similar to the oxygen structure, which is shown in the bottom right here. So we know that this is nebular helium-2 that we are observing, and it is the gas that we're seeing this helium-2 come from. When we take that amazing COS spectrum, we're actually able to fit the stellar populations that are driving this galaxy. So these stellar populations that dominate in the UV tell us that the ages of these galaxies, the ages of the stars in these galaxies are 1 to 10 megayears. So they are the very young stars. And the metallicity for these stellar populations is somewhere around 10% or less. So these are good analogs to the Reionization-Era galaxies we're hoping to find. We're hoping that you see with JWST. When we take that stellar population and we plot its ionizing spectrum, we see that on the very left here is where the photons would be that you need to create helium-2. So even with the stars that we are seeing in these galaxies, it looks like we might not have enough ionizing spectrum to create the helium-2 we observe. So that's what we want to test. And to do that testing, we are going to use photoionization modeling. So photoionization modeling, we start with the most basic level of this, where we take cloudy and we put in a single age burst of star formation that we get from BPAS. When we do this, we're going to get a number of these lines from emission lines, and we're looking at these kind of complicated plots, so I'll go into depth a little bit more. On the x-axis, we have log U. Log U is a measure of the hardness of this radiation field. So high energy hard ionizing spectrums are going to be on the right, and less energetic things are going to be happening on the left. Then we have the line ratio on the y-axis, and this is allowing us to compare lines across galaxies. And we're comparing everything here to H beta. Then we can look at the models that are on these galaxies, on these plots, and they're the colorful lines in these plots. So these lines are the width from the different ages of the stellar bursts, star formation bursts that we tried. And what's most important is the different colors are metallicity, but these models are peaking on the left-hand side for these low energy, these low ionization species. And then they start to peak further into the center of the plots. And when by the time you get to high ionization lines, they're peaking on the right side of the plot, except for helium-2, which peaks nowhere on this plot. So that's not a good sign for these reproducing observations, which is what we check next. So we compare these models to the observations of other small metal poor galaxies nearby, and we can see that the top panel, the points all fall within the band of where the models can predict these line ratios to fall for anything in the top panel. So low and intermediate ionization lines are reproduced by these models. But when we get to the high ionization lines, the points start to fall off of the model prediction area. And we get to the helium-2, and the models are nowhere near these observed helium-2 line ratios. So this is telling us that a single age burst of star formation is good at reproducing the low ionization lines, but not at reproducing high ionization lines. They're under predicting those high ionization lines. So we need to level up our photoionization modeling to the next level. If we want to reproduce everything, we're going to try, instead of a single age burst of star formation, we'd rather try the stars that are actually in these galaxies. And so to do this, we take that stellar continuum fit that I showed you earlier from the UV spectrum, and we use that as the input for our photoionization modeling in Cloudy. When we do this, we're still able to reproduce the low and intermediate ionization zones, but now we can also reproduce the high ionization zones. So this black dashed line that runs through the center of these bands is telling you the observed metallicity, and you see that the observed metallicity model is very close to those points that we see that are the observed line ratios. So this is good news for the stars, except when we get to the high ionization lines, we're still not able to reproduce the helium-2 or oxygen-4 that we see in these galaxies. So even with just the stars that we observe, we're not getting enough photons to ionize helium-2. So we need to level up our modeling again. And to do this, we add a black body. So we are not physically figuring out what the mechanism is that causes the helium-2 right now. We just want to know what temperature and contribution to the flux is needed in order to get to the photons we need for ionizing helium-2. And so still, when we add a black body, we can still produce low, intermediate, and high ionization lines, but now the band for the models is able to encompass the points for helium-2 and oxygen-4. So this problem of reproducing the very highest ionization lines is now something that we have created a black body to fix. And again, just to show you, the top model here, top panels here just show you the model including only stars. And now we're able to reproduce the highest ionization lines with an additional black body. Our black body is characterized by two parameters. We have the temperature, which is mostly determined by these lower ionization lines on the left, as they have a little bit more information about what temperature is needed to create their emission lines. And then on the right, we have this additional parameter that is the contribution to the flux. And so each of these additional lines that you see on this plot are an additional 10% contribution to the flux. So this tells us how much of the total flux this black body needs to be. So when we take these two parameters, we are actually able to tell you that the ionizing spectrum for these galaxies, in order to reproduce their highest emission lines, you need to add an 80,000 Kelvin black body at 60 to 70% of the luminosity of the young stars. So this is a significant fraction that really changes the shape of your ionizing spectrum. And so these dots show you that without the addition of a black body, we have essentially no photons that are getting us helium-2, and now we have the photons available to give us helium-2 in these galaxies. And now the question really becomes, where are we missing the stellar astrophysics? We've just added a black body and we don't know what this is. So there are a number of options that have been suggested in the literature, things like low metallicity stellar atmospheres and Grace was just talking about low metallicity stars, our models do not really account for the very lowest metallicity stars, and so it could be that our stellar populations are just a little bit incorrect, like Grace was talking about. There's also very massive stars, stripped stars, Wolf-Rayet A's, things that low metallicity that have never really been seen. Also shocks and ultraluminous X-ray sources. A number of these things have been suggested, and then also we have upcoming X-ray data, so it helps us to know whether or not these are the options. But if you have other suggestions for what this black body could be, we would love to hear. So again, your stars are not going to reproduce the helium-2 that you see unless our models are incorrect. Instead, we need to add a black body to those stellar models in order to get us the helium-2 and other high ionization lines that we observe. So with that, I'll take all of your suggestions and any questions that you have. Thank you for your attention.
Thank you very much, Grace, for an interesting talk. Just wait a minute while people come up with and type their questions. The last one while we're waiting, just wondering where potential like weak AGN contribution could fit in to match some of these emission lines.
Definitely. So we've checked the BPT versions that we have of these line ratios and things, and they do still look like they fall into generally star forming areas of the BPT diagram. However, it could be that there are weak AGN in these things. They are very, very small though, with stellar masses of something like 10 to the 6.5-ish of stars. So it would be a question for that. We do have X-ray data that we could look for that we could see if there's some other high energy thing in there. So we will check. So far though, it doesn't look like we have any extra sources on that galaxy, those X-ray sort of detections.
Okay, great. Thank you. So while we were talking, now we have some good questions. So the first one is, are these young stellar populations still embedded in their birth clouds?
So that's a good question. We have a little bit of information just by the reddening to these galaxies. We don't know for sure, and it doesn't totally look like they are really embedded in their natal clouds still. We are not doing any additional modeling to account for that. We are just assuming they are in this H2 region-like structure that is not fully dense material. I think we have H1 data for these galaxies, but aren't seeing anything crazy.
Okay, thanks. There's another question. You add now this black body, and what observations do you think we could do to distinguish between all these different possibilities that you're listing here? Yeah,
that's a good question. So we have X-ray data coming up. If we could get farther into the UV than our current data actually has from COS, we could get a little bit closer to seeing that difference in the ionizing spectrum. And also there are some additional emission lines that we're looking for. Things like oxygen 6 can rule out things like a suppressed superwind and catastrophic cooling. So there are a number of emission lines that we're looking forward to getting that we don't already have that could help us eliminate some of our possibilities.
Great. I'll ask another question. What implication would this model now have for strong carbon-3 emission that we're seeing in galaxies?
So that's a good question. Our carbon-3 is a little bit of a question right now because it's not completely fit by our models at the moment. Mostly this is a question of it's not in the highest resolution spectrum that we have. The carbon, if this additional source could produce extreme carbon-3 as well, just with the high energy photons that we have. So this could relate to that emission that we're seeing elsewhere.
Okay, excellent. I think we're perfectly on time. You have more questions on Slack. Thank you, Grace.
All right, thanks.